level languages where you describe things out at this kind of functional level as opposed to the code level, making it easier to take advantage of really cool and advanced software, the hardware. So classic, you synthesize gate level circuits from these higher level models, and it's going to enable really cool, large scale quantum circuits, but it's much more than a new programming language, and that's kind of where the analogy stops between our company and others who are trying to do much the same thing in the field. When you're programming quantum computers, and we saw this yesterday, you have to define what you want to do. You have to find an algorithm that'll do that, right? Is it Shor's? Is it Grover's? Is it a quantum Fourier transform adder? You have to figure out what are the algorithms available to you that can do that functionality. You need to modify that algorithm for that use case. You need to optimize your circuit based on everything we were talking about before, right? Qubits, depth, gate sets. And then the automatic part is when you hand that to the computer, it'll do some transpilation and kind of transfer your circuit to something that can run on that computer, because not every computer has the connectivity we were talking about. Not every computer has all the rotations that you programmed in the system. In fact, one of the things that our CTO likes to say at Classic is that quantum software is easy to define but hard to implement. Right? It's easy to talk about Grover's algorithm. It's easy to talk about Shor's algorithm. It's much, much harder to program that into a system. And so there's all these system level constraints, right? You have block level decisions, system-wide constraints, and they're all deeply interconnected. If you want fewer qubits, you have a longer circuit. If you have a longer circuit, that means you have more error in your system, right? And the hardware right now, gate sets, noise modeling, it takes a lot of foundational knowledge to program quantum computers. And so what Classic's doing is we call it essentially design automation, quantum circuit design automation. We're automating the process of programming these quantum computers. As a user of the platform, all you need to know is what you want the system to do. And the platform itself will figure out the how, right? How to implement it. It'll figure out the algorithms. It'll figure out, how to adapt that for your use case. It'll optimize that circuit for whatever optimization parameters you give it, right? If it's the hardware you want to run on, if it's optimized for the number of qubits, try and make that as small as possible. It'll do that. And then it'll send it over to the compiler transpiler. So making much more of the process automatic and essentially just making it easier to program quantum computers. You can come into the show with much less foundational knowledge, right? You don't need to have a PhD level to go ahead and start programming quantum computers. Certainly, it can never hurt. But you can start having software engineers learn this, develop software in your companies. This is kind of a fun diagram of our full workflow. We have our model. You define your constraints. It gets automatically generated, right? You get your fun circuit, and we'll see that later. And then you can output to the assembly language of your choice. Now, that's huge, right? Nobody wants to program in one language. No company wants to just use IBM, right? They want to try out Amazon. They want to try out all these other hardware. They don't want to be pigeonholed into one vendor or one solution. They want that flexibility because no one's really sure which hardware vendor is going to win the race. So having these things at this higher level language is quite attractive for a number of companies, and certainly just makes everyone's lives easier to program quantum computers. And so, this system and most platforms that you'll be using will work with most any kind of gate level cloud computing quantum computer. Right? We talked about there are some other quantum computers. You can buy quantum computers. They're not in the cloud, but certainly. Thank you, Amazon and IBM and everyone else who put quantum computers on the cloud. Makes it much easier to access and use, and makes it not as expensive, right? You don't need to buy one of these D-Wave, $15 million computers to use quantum computing. And so, the classic solution, I'm kind of breezing through this so we can have lunch. We have three parts to it, right? We have this high-level modeling, right? There's this dynamic language. With that dynamic language, it'll automatically generate your quantum circuit, so it just outputs for you. You don't have to be there at this gate level. How do I get from 0 to plus and rotate? You don't have to worry about that. And then there's circuit analysis, right? Because coding doesn't stop at I generated the code. You need some way to analyze it, debug it, model it, view it, right, to figure out is it running? Is it running effectively? How can I fix this? And so, we've developed this whole workflow to be very similar to how you would program classical computers, right? You have this vision, you develop your file, you compile it or assemble it in classical computer. We call it synthesize for classic. You would execute it on your hardware, or you figure out which cloud vendor you want to execute your software on. You analyze the results and you figure out, okay, do I need to debug this? Do I want to optimize a certain parameter? Did it take too long to run? Maybe I want to make it shorter. Was there too much error? And you can kind of go through these iterative processes, and then once you're done, you release that software and you're good to go. Essentially, what the classic software allows you to do is focus on what you want to do instead of that kind of minutia how. It reduces the number of resources you need to use for a quantum computer because it automatically figures out how to do that optimization for you. And that's actually a big deal, right? Because quantum computers are the size they are today. So if you want to run on the hardware of today, you need to make sure, how do I fit my problem into those constraints? And again, that's not a trivial thing to do. Right, definitely developing the resource time, right? It would take me a couple of months to generate something on 50, 100, 1,000 qubits. We'll have fun using the classic platform. In minutes you'll be generating 50 qubit circuits, no problem. And because it's a lot easier, you can start bringing in domain experts, right? If you're trying to do a financial application, a financial quantum algorithm, you can start bringing in your finance experts to say, what are the calculations we use? Let's start plugging that into the software. You can start bringing in your domain experts in the fields that you're trying to solve problems for. And you can definitely create new intellectual property with this as well, since we're defining things at the functional level as opposed to this kind of gate level design. That is a patent, right? That is a utility patent. Use this algorithm, then this algorithm, then this algorithm for this output. That's how patents are written. And so if you define a really cool algorithm in the system that works out for you, it's really easy to just go ahead and kind of cut and paste and send that to your legal department and have them help you out with claims language. So that is the classic platform, and I'm much more about show than tell. So I'm going to have a lot of fun, walking you through the workshop later today on using the classic platform, because that's absolutely the fun of it. And I'll say let's break for lunch. All right. Woo. Cool. So here's my installers, but I'm already all installed here. I'm going to do all my imports of plotting. So that's just so when we get to our results, we can plot it out nicely. I'm going to load in all those classic imports so I don't have to do that again somewhere in the system. I'm going to go ahead and authenticate myself. It says I'm already authenticated, so stop trying to do that. And so in these higher-level programming languages, right, what we're doing here is showing you the basic modeling concept. Here we say we have a probability distribution. We have 4 probabilities, 0.5, 0, 0, and 0.5. Has to add up to 1, so good. We're calling out a parameter called state preparation, and we want the probabilities to be in a probability mass function, like we typed it out. Those probabilities listed in a row. And we have a certain error metric. So you could say, how accurately do you want your probabilities to align with what you typed in, right? That goes along with how closely do you want that arrow pointing where you want to on that sphere. If you want it to be more accurate, it's going to be a longer circuit. If you want it to be, if you're okay with less accurate, you'll get a much shorter circuit there.
Yeah, but just one thing, those probabilities, right? You remember when we said...
Talk about that for a second.
Yesterday we said that when we have 2 qubits, right, we have 4 combinations that we can have, right? So you have 0, 0 state, 0, 1, 1, 0, and 1, 1, right? So the probabilities that you see on the top, right, 0.5, 0, 0, 5, basically means we want to start, right, where we have 50% of the amplitude or the chance of being in here, and 50% of the chance is being here.
Always those probability must be normalized, like
you want probability to add up to 1, right? Because if it's less than 1, it means that you don't cover all the possible outcomes, and if it's more than 1, it means that something can happen twice or like something like that, right? And again, just to connect it to what we did yesterday, you remember when we started with 2 qubits, we said that we start in this place, right? But when we wanted to get here, what we actually had to do yesterday, right, was to somehow apply Hadamard gates and NOT gates, right? All this kind of stuff, to somehow eventually land at this place. So yesterday we had to think about all the operations and rotations and entanglement, superposition that we need to create. Here you just tell the system, make it 50%, 50%. It will figure out how to do it for you.
All the text on the bottom here is all just coding to tell the system to generate that circuit, right? Model designer is the call you make to send this information to our model designer. We then tell it to execute the state preparation. Cool. And we're telling it to synthesize that circuit and then show that circuit. So all the input parameters are just, here's your probabilities. What do you want that error to be for your circuit? So I'm just going to click enter here. Expired token. It's fine. Wah, wah. Doesn't like my tokens. Let's go. All right. So it's popping up the analyzer here. So this is the same page if you went to platform.classic.io. The Python SDK will kick you right into the system to show you that generated circuit. And it's just taking a hot second to load up on here. But here we go. Here's our 2-qubit circuit. You can load it. Here's our state preparation. There you go. We have the whole thing here. All set and done nicely. Just a very, very small circuit, but again, you didn't have to figure out how do I make these probabilities match the thing. The system handles that for you.
One thing I wanted to notice, right? Initially, it draw the circuit with one block, right? State preparation. It doesn't tell you what is going inside, right? This is part of the abstraction that you're trying to create, right? You don't, if you're interested, you can see how it's actually implemented with a Hadamard gate and a CNOT gate, but other than that, you put a block, right? Prepare the state for me, right? And this makes it more human language kind of way of thinking about it.
Absolutely. It makes it much easier to understand some of these very large circuits because it chunks out certain portions of it so you understand, okay, this bit of the circuit is doing this bit of the circuit is doing that, okay. Instead of just having gates. Yeah.
Understanding the logic behind
Yes.
this and the whole component.
Yeah.
Why these operations matter in terms of calculate some outcome? This is something that I didn't get it because in binary it's quite simple. I change to a state and that will give me a result that can be a sum or a subtraction. I can convert that in math. How that I convert those states in actual math or in actual calculations?
So,
This is the part that I cannot connect.
so you remember, so first of all, two things. We agreed, we created ASCII, right? And we decided that if you have 110111, it's equivalent to the letter A, small a. We chose it, right? Then the computer is doing its calculation based on our definition. Now you ask how it comes in play here. You remember yesterday when we did the optimization problem for the portfolio, we built the problem and the algorithm and everything such that when you get 1, it means you need to pick this stock, and when it says 0, you don't pick this stock. Right? So you need to design the problem, the algorithm, and think about what the output will be such that it has meaning to you. Right?
So I have to present the definitions that what will be that state.
Yep, and there's a couple of fun examples we'll get to that show you how to read that binary and how it translates to actual solutions. Perfect. Okay, so we saw that code. We're just going to go ahead and execute that code and print out the results to see what that looks like. So we're actually running this circuit. It's not just abstract. And we got 2 bins. 50%, 50%. Perfect.
So like say 50% here,
Yep.
50% here.
Exactly how we wanted it. And you didn't have to figure out all that arrow stuff. So this is an example showing you that you can do much the same with amplitudes as opposed to a probability mass function. And this is important to be able to load in your probabilities in different ways because certain applications are going to need Gaussian profiles if you're trying to match kind of the shape of a stock's distribution over time. things like that. So you need to figure out having a robust system that can input your probabilities in different ways. So thankfully, it's just a matter of saying I have amplitudes, or I have a Gaussian profile, or I have a probability mass function. This is what I want it to be, and generate for me that circuit.
It's working. They fixed apparently the authentication code. So
Yeah.
now we can access to the token.
Okay. Absolutely no. Good.
Wait, can you get to what they're on? Because I
Okay.
keep on clicking, because I also
Okay.
got it, but I keep always.
So I just want to check, anybody who's having authentication issues, if you can try that one more time. It looks like for some people it's clearing up.
I'm just gonna listen.
No problem, yeah, totally. Yeah,
Yeah.
cool. All right, so here is the bit about arithmetic that we were talking about, and you can see how those results from the quantum bit string turn into actual results. So here we have these two states, and we want to first prepare these states, and then we want to do addition with these states. So we have state 0, 0 and a state 0, 1. And we're going to call these, right, state 0, 0, the wave function 0, 0 and 0, 1. We're going to say the first bit is 0, that last bit is the number 3, and again, we're defining what these combinations of bits mean for us. So here we're giving them definable values. So we're saying 0, 3, 1, 2. And here it is, right? We have 50%, 50%.
Like,
Exactly, so we're saying, what was it? 0, 1, 2, 3 is what we're calling it. Exactly.
right? So to make it even more compact, right? Instead of, right? Because if you'll have like 10 qubits, it means you need to write 10 numbers one after the other. So now let's make it even more simple. Let's code, let's say this one, now we call it state 0. This one we call it 1. This one we call it 2. And this one we call it 3. And if you think about like what is the logic behind it, this is binary counter, right? This is the binary representation of the number 0. This is the binary representation of the number 1, right? So let's say we want to count to higher numbers. If we add a third qubit, right, with 3 qubits, you can actually get to 1, 1, 1, right? And you can count all the way up to, in this case, 7. Right? You want to grow to larger numbers, just add more qubits, and you can count this way. So it's a nice trick, but this is how you assign meaning to those zeros and ones, right?
So that's the first part of the puzzle. We're defining this to be our state functions. We're just going to use binary notation to give them a value that we can start doing computation around.
I have a question.
Yeah.
So you have like the sphere, and you have the x-axis, which is the -1 and 1, and the z-axis, which is the imaginary axis, right?
Z we define as 1 and 0. The x-axis we define as plus minus, and the y-axis we define as that imaginary plane.
So I'm trying to figure out whether the 0, 0 and 0, 1 are just like different representation of minus x, plus x, minus z, plus z.
Whenever you're seeing 0 and 1, and most of the notation you're going to see is in 0 and 1, that's always that z-axis, because that's the plane that we're measuring in.
Right.
And so we tend to translate all of our states, all of our preparations into this z-axis, because that's how we're going to measure it at the end of the day. So we want to prepare it in a certain z-axis. We'll do fun rotations, and then we'll measure it at the end in that z-axis.
So it's like something like this.
Yeah.
So 0, 0 is plus z.
Yeah, 0, 0 is both of them up. 1, 1 would be both down.
Both down.
Yeah, so then it's this, that.
But again, we chose to call it this.
Yeah, I totally understand the both.
Yeah.
So why don't we use like different representation with the imaginary states? Like the electrons can spin not only in the.
Yeah, so the y-axis is important when you want to think about it. Eventually, we're talking about waves, right? Schrodinger equation, it's a wave function. So it
Okay.
has properties not just of particles, also waves. And waves can have a phase shift, right? So if you think about like sinus and cosine, right? They are the exact same function, it's just shifted by pi over 2, right? So you can think about if you want the wave that you describe, not just to have different heights and width and stuff, you want it to shift in phase, then you use the y-axis because it gives, imagine like a phase.
Yeah.
So you can move stuff backward and forward, kind of.
Cool. Hopefully that helped. Yeah, and all throughout your calculation, right, when you're doing your algorithm, you're going to be using these other planes. It's just that when we measure it, we're always doing it back in Z. And so your results will always be back in a 0 or 1 space. And that's just uniformity of language so that everybody agrees this is how we're measuring it, everyone agrees this is how we're talking about it, and at least, you know, the quantum community has agreed at this kind of basis, right? One computer is not going to be measuring in plus minus and the other one's measuring in up down. We're all agreeing, let's all work in this Z axis. We'll prepare in Z, we'll measure in Z. So when I use an algorithm and I want to build it for one and another, it's not just changing the assembly language. It would be terrible if you have to change the basis set also. That's too much. So here we're just, again, loading in these probabilities, right? 50%, 50% for 1, 0, 3, 50% for the middle two, 1 and 2. I'm going to tell the system, generate these models for me. It did it, perfect. And then I'm going to go ahead and put these into an adder. So we have an adder, we have a left argument, a right argument. You have to put in how many qubits are going to be going into this. So I'm saying each of them have 2 qubits going into my adder. And those are connected to my SP1, my state preparation 1, and that's connected to my state preparation 2. Perfect. Gonna go ahead and run that. And then I'm just gonna say, please synthesize this circuit for me and show me what that looks like. Again, I'm not defining anything at this gate level, I'm simply saying, I have a state preparation, I want to add them. And you're drawing it out and you're defining it as if you're doing a circuit diagram. I have a wire going into this. And the system is going to figure out how do I make this circuit diagram that you're defining, right? Wire into an addition, right? Functionally into this gate level. All right. So here's our circuit. When you open it up, you can see yep, 2 state preparations going into an adder. Again, right, we're chunking it out so we can see what this is at a higher level. But you can open this up and see what is it? What makes up an adder? If you try to program an adder by hand, it's a whole bunch of rotations and quantum Fourier transforms. And you can see what is a quantum Fourier transform. Well, that's even more fundamental, you know, different blocks and gates. You can see what those state preparations took to get there.
Preparation, this code is based on which machine? ABM?
No, this one is simply the code itself. We're saying, I want to prepare this, and then I want to go ahead and do an addition. We're not giving it any optimization properties, but I'll show you that in a little bit.
Because it has several ways to achieve the same outcome.
Yeah, there are different ways to do addition, absolutely, right? This is using what's called a quantum Fourier transform adder. There's also what's called a ripple carry adder. There's 2 implementations for addition that you can choose between. And I'll show you those optimizations in just a little bit. So that's your circuit here. Generated it nicely. Let's keep going and let's execute it, right? Let's go ahead and run this circuit that we just did. So here we're gonna execute it, doing it 1,000 times. And here's our circuit. So here's our solutions. We have 4 bins, cool. But what does that mean? So let's go ahead and print out this result in a human readable way. And here is our arguments. We have these 4 solutions, right? So we have 0, 0, 1, 0, 0, 0, 1 is one of our bins. Well, what does that translate into, right? So it translates into 1 plus 0 equals 1. And that is that bit string and how it's being read by the computer, right? these solutions, and this is how it translates for you, right? So what 1, 0, 0, 1, 1, 0, 1 is 1 plus 3 equals 4, and we're kind of reading it backwards almost, right? So we have to go ahead and say, split that in half, the 1, 0, 0, and the 1, 1, 0, 0, 1 and 1, 0, 1 are two different sides of the equation. 1, 0, 1 is your result, and the everything before that, the 1, 0, the 0, 1 are the inputs. Yes.
So the right argument and the left arguments are the two numbers that are being added to the result? Or,
Yes.
And that gives the result. Okay.
And that's how essentially you can interpret these results, right? We have essentially we have the entangled states and then the solution for that equation going through the adder. We're telling the system entangle these, okay, boom, boom, we have these two. What does that do for us at the end of the day?
And
Yeah.
so why do we have equal probabilities roughly for all four states?
Oh, great question, because what we did was we added up 0, 3 with 1, 2. So all the combinations of those additions.
Oh, okay,
And that's kind of the power of quantum computing. It was able to do all of those additions
right.
in an algorithm.
Okay.
Wait, sorry, could you repeat?
Can you explain that again?
Yeah.
Yeah.
Why is 0, 3 and then 2, 1 again?
So you want to, yeah.
We gave as an input two states, right? We had the state 0, 0 and 0, 1, I think, right? And we defined them, so we said, okay, I want you to add argument number 1 with argument number 2, right? This one was defined as 0 plus 3. And that's, so this is 1, and now you want to add this one. This one we called it, we defined it as 1 plus 2, right? So we had 1 plus 2. And now, because of this superposition, because of this is actually the advantage that people are talking about, it's not just adding these two. It says, okay, I have, if you recall, I have 50% chance of being here and 50% chance of being here. So and it also goes for these two, right? Because we define it like I'm 50% here and 50% here for this argument, and 50% here and 50% here for this argument. Right, so 50% of the times I had 0 plus 1. Now it's 0.5 times 0.5, 25%, right? 25% of the times, the input that I got for the left one was 0 with 1, 25% I got 0 with 2, 25% I got 3 with 1, and 25% I got 3 with 2. And if you look at the results, it's about 25% for each. And because of those weights, we actually got all of these combinations, right? If, for example, we wanted to just add 1 plus 3, right? We should have prepared a system that we have 0 chance of being here, 100% chance of being at 3, 100% chance of being here, and 0% chance of being here. Then, for certainty, we would add this one with this one. So we get just one column saying 3 plus 1 equals 4.
How can you check the certainty?
We have, if you, Eric, scroll up to the top, you see we defined probes 1 and probes 2. Right, so these are the probabilities. So you see probes 1 defines the first one. We said give it 50% chance for this guy, 0% for this one, 0% for this one, and another 50% chance here. So you actually got 50-50 for these two. For the second one, we said 0 for this one, 50% here, 50% here, and 0 here. So we got 50-50 on 1 and 2. And then the probability is kind of, you know, sometimes you pick these two, sometimes you pick these two, and you get all of those combinations all together. You can take advantage of it if you want to add stuff that you care about. If you want to know all the 4 answers, you did it in one calculation technically. If you want just a subset, you can adjust the probabilities to make sure that it will just calculate what you care about. Right? So this is part of the design of the algorithm.
Perfect, right? Essentially what an addition circuit does, right? We have the 2 state preparations and then that addition function. It turns the rest of that bit string into the addition of the first 2 entangled states. That's its entire function. It looks at those first 2 entangled states and intelligently makes the rest of that bit string be the addition of those, regardless of which of those probabilistic outcomes it comes out to be. Cool. All right, so we got to here. We have a fun kind of do-it-yourself circuit here, but I'll just plug it in. And this was to figure out essentially doing the same thing, but for multiplication. So I'll just go ahead and do this all in one shot. And in the notebooks are also the solution, just because I just want people figuring out how to do all the inputs for it. But let's go ahead and plug that in. So again, we have 2 different state preparations. Going ahead and doing this, right? State prep, multiplier.
You can see like this is like a nice example, right? The state preparation for the first input, it's relatively short. The second one, it's much more difficult, even though it's again 50% chance you split between 2 of them. But apparently picking these 2 is more difficult than picking these 2. Right? So if you care about like actually digging into the code and understanding what was going on there and how you prepare it, you can see it. But if all you care about is building a software, building an application, it's like you define functions, right? When you define a function state preparation, you give the input, right? You define the function in the beginning of your code, and then you just call the function. You don't care what it's doing, right? So it's the same idea here. You just have a block that is doing whatever you told it to do.
Exactly. Yep. And in this state, we're going ahead and multiplying 0 and 2 with 1 and 2. And you go ahead and see 1 times 0 is 0, 1 times 2 is 2, 2 times 0 is 0, and 2 times 2 is 4. Perfect. We have a quantum system that is doing good mathematics. And again, right, we did all that in a single, well, with 1,000 shots, but we did it in one calculation, right? We didn't need a different calculation for each of these different inputs, right? Each of these different variables. Let's go ahead. Okay, so that's essentially how you would set up some of these problems in the platform. That's kind of the power of having higher level languages in general. To be able to do some of this, but the real power of some of the more advanced systems, and I'm biased because I really like my company and my software, but some of the benefits of some of these, more robust systems is the ability to optimize dynamically for you. You don't have to figure out how to optimize for one thing or the other. You can just tell the system your constraints, and it will do the optimization for you. It'll modify those same circuits to whatever your criteria are. So here's a system where I have a probability mass function again, just what are my probabilities? As long as I make sure they add up to 1, then we're good. And I'm just putting a simple bit of code saying, do this 5 times for me, right? Iterate 5 times, generate the same exact thing. Then I'm going to go ahead and synthesize and show it. Perfect. All right, so here's our whole circuit. Here is our 5 state preparations. all next to each other. And this is a part of the analysis of your circuit, right? You could deep dive into each of these sections, but it easily tells you the depth of your circuit is 55. So there's 55 time steps in here. Deep dive into each of these sections and click on these and kind of see all the minutia of it. But here is our state preparation 5 times, this very long circuit for preparing those states. And then I'm going to go ahead and print out what is that depth, as we just saw, is 55, and what's the qubit count? Cool. Now, what happens?
Maybe we didn't
What's up?
like explicitly say that, right? But there are 2 dimensions that you have for a circuit, right? You have how long, or we call it how deep, the depth. This is what Eric mentioned, like the depth is 50. It means that along those lines, you had 50 different operations, right? So you think about this axis as the time axis, right? And how many qubits do I need to use? We call it the width of the circuit, right? So the more qubits you have, the circuit is wider. So it's wide and deep.
Mm-hmm. Thank you. Sometimes I get so caught in my lingo that I forget. Yeah, and certainly, right, width is a function of the system you're running on, right? You can't have a larger width circuit than there are qubits on the computer you're trying to run on. So often you want to limit the number of qubits to be the number of qubits on that system and try and optimize for that depth, because right now these qubits are noisy. So you want to try and truncate the circuit to be as efficient as possible so you have efficient calculations. So here what we're telling the system is, I want a constraint. I'm not changing anything about the model I gave it. All I'm doing is saying, do that same exact model I gave you. Same exact probability, same exact circuit, but I have a constraint now. Try and do this with fewer qubits, right? We had 20 qubits that it took. I'm saying I have 18 maximum. My computer only has 18, do something for me. And so the system's going to go ahead and send that up to our servers. Essentially on the back end is a giant constraint satisfaction problem that it's trying to solve. And it finds a solution that meets those constraints. And here you go. So what it was able to do was truncate this circuit to be actually within 16 qubits. And the way it did that was it reused what's called auxiliary qubits. Often in these calculations or in a lot of these functions, you use an extra qubit to do some of the math. But then after the operation's done, it's freed up. It's a freely accessible qubit that's not doing anything for the rest of the circuit. So you can intelligently reuse these auxiliary qubits to truncate your circuit and have it essentially be less wide.
It's like when you have cache memory, right? You can store some of the information, use it. When you're done, you just dump memory, and then you can reuse the memory for other calculations, right? So you can do the same thing with qubits. You can kind of use them as memory for part of your system.
Mm-hmm. So here's all this, but you can also just go ahead and let's see, blow it out to all of its fundamental parts and see that circuit that you build. Certainly don't want to be doing this by hand. And yeah, let's see, what's the output? All right, so now our circuit depth, our qubit count's 16, cool, we got within that, but our depth is huge now, right? Compared to a depth of 55, now we're at 227 time steps. Well, we can also tell the system, instead of that, let's go ahead and optimize for, instead of saying, I have this many qubits, you can always tell the system just optimize for the number of qubits. What you're going to see in the system is it actually comes out with the same solution, 16, but you didn't have to specify the number, just optimize for this parameter. And you can also mix these parameters. I can say I have a maximum width of 16, optimize for the depth for me. So again, I haven't touched the model. I haven't touched telling the system what the circuit itself does. All I'm doing is changing the optimization parameters, and it's giving me different circuits that meets that optimization. I didn't have to figure out how do I reconfigure these state preparations to fit in the thing I'm trying to do.
So,
yeah.
if we both have different answers, then it's normal because there are different solutions to the optimization problem? Or?
Absolutely, yeah. So what will happen is the system actually picks out a random seed to start investigating this giant multivariable, vector space essentially.
So my seed was better than yours. because I only utilized 50 qubits.
Perfect.
Okay. Right.
So let's go ahead and see this.
So it's just not 50%.
And here we go. So it went ahead and gave me a different circuit altogether. And let's go ahead and investigate it. Okay, so
I think like
Yep.
we can make like a funny comment here, but the reason you ran it several times and you got a better answer is because probably it's not the optimal. There is the best circuit that you can get. A classical computer uses different ways to investigate around this, where the seed comes in, but had you been doing the optimization on a quantum computer, you would both converge to the single circuit, which is the best.
Okay.
we'll get there eventually. Optimizing quantum circuits on quantum circuits.
Yeah, we're already letting AI design classical computers.
Why not? You know, I got to use Chat GPT to see if they can create quantum circuits for me. I haven't tested that. It could make code. I just haven't checked quantum code.
Like you might be out of business.
Oh no, yeah, let's not check that actually, no. But here we were able to see that we were able to optimize within the max width that we could constrain 16, and we have a smaller circuit, 106 compared to the 227 we had before. So you can go ahead and mix these optimizations to fit what you're trying to fit it in. You can also do that for the number of gates. So this is just a quick example. I won't even run it, just saying, if you have a maximum number of gates of a certain type, you can absolutely do that too, right? Multi-qubit gates tend to be more difficult for quantum computers to handle, to keep it short. So sometimes limiting the number of multi-qubit gates often increases the efficiency of your calculation. So here we would just say, right, what is my constraint? Well, my constraint is I have 160 C0 gates, don't use more than that. Okay, and it'll give you a circuit using no more than 160 of these. Perfect, all right, so there's also the flexibility of this error that we're talking about, right? So here we're gonna be putting in 3 Gaussian distributions. Again, just showing off the different ways you can put in probabilities. I'm saying that for the first one I have, for both of them I have 8 qubits to do, essentially to map our Gaussian distributions onto. But for the first one I have an error rate of 0.08, and the second one I have an error rate of 0.001, so much more tight. I want those circuits to show up to, so we're going to show what that more lax error constraint is. How do you map these Gaussian distributions to these qubits? All right, let's take a look at it. All right, it's a depth of 30 here, you can see that. And let's go ahead and do this tighter constraint, 0.001, right? Again, the same distributions. Sometimes your calculation, you might want a more accurate answer, a little bit closer to what you're exactly looking for, and you might want that tighter tolerance so you can have real crisp and good answers, but you're gonna have to sacrifice something for that, right? So what we're gonna see is the circuit's gonna come back, and it's not gonna be a friendly circuit because it's 6,309 deep. So that's a lot of scrolling here, right? Just for a little bit more accuracy.
So when you said there's error, it means what does it mean when you say there's error?
Yeah, so how accurately are you mapping the probability to the distribution you're looking for? Like
So Gauss is what 0 and 1, isn't it?
yeah, let me show you on a graph here. So essentially what we're doing with these histograms, with these states, right, if you were to, do 1,000 shots, you have, 0, 0, you have 0, 1, and likewise, if you have a Gaussian distribution and you want the distribution to be, something, that's a terrible Gaussian, but sure, you want the bars to as closely approximate this as possible. And so the more qubits you use, the closer you can approximate, or the more depth you have. You can make sure that this is as close to hitting that point on the line as possible. And so, right, how far away you are from that is kind of your error rate on that. Now, how closely are you mapping?
So the lower the error, the more the depth? Is that-
Yes, because the lower the error, the closer it is to the exact, and that just takes more computation, right?
Okay.
Yeah.
And but just visualizing this as more computation means more bars because there's more shots.
for what we're talking about, it's about that block sphere, right? How accurately can we point to the exact position we want with that exact probability?
Okay, so you keep trying. In this state, you keep trying until the
Exactly.
error rate is within the limit we want, right?
Yeah, so right,
Okay.
this is number of shots, but you can also think about it as your probability, right?
Yeah.
And so you can say if this is supposed to be 48.2 on the dot, to map that properly, to get this state to be at 48.2 requires more tweaking of that block sphere to get it exactly there, right? You might get to 48, but if that's more than your error, it has to try and get a little bit closer, 48.1 with a couple of more rotations.
Can I understand it as when you say depth, you mean the number of solutions, and qubit then means what?
When I say depth, I mean the number of operations occurring on that qubit.
Okay.
What does the width represent?
The width is the number of qubits. So again, like we showed, the width is this dimension here, right? So you have your 0 qubit, 1, 2, 3, 4, how wide that circuit is drawn.
Is there a limit?
A limit? No.
So if the constraint is too big or too small, like if the width is too small, the constraint is too big, then what does can there be no solutions?
Absolutely, that happens quite frequently, right? You try and do, it happens to me when I try and do Grover's algorithms. I try and solve a large algebraic expression using Grover's that searches this data set and can find solutions for you quite nicely. I can show an example of that. And I'll say I have 5 qubits, and it's going to say, nope, can't do it. The thing you're trying to do is not possible on 5 qubits. Please relax your constraints. The system will give you that no.
Okay.
Yeah. And that's often why, when I program using the classic platform, I tend not to give it exact numbers for number of qubits or width. I just say optimize for these parameters, and it'll try to get me as short as possible.
Okay.
Yeah. So that way I can see, for this calculation, what are my resources needed to run this? All right, so I'm just going to go ahead and print these results out, right? We saw same amount of qubits, but that depth gets big. We can go ahead and execute both of these as well, both of them with 1,000 shots. And afterwards, I'm just going to go ahead and essentially plot the distribution out to the curvature. And we can see how closely these match up. Here we go. All right, so you see that the orange bar maps quite nicely to the distribution, the 2 Gaussians or the several Gaussian distributions we put in there. But the blue line kind of dips down on that second large peak as opposed to mapping out along with it. That's within the error parameter we gave it, but if you actually wanted it to be exactly right, that's not going to cut it, right? You need that deeper circuit, the more operations to get your mapping exactly where you want it to be. And again, right, trying to figure out how to do that by hand, qubit by qubit, that's not the easiest, right? It's not intuitive how to do this. And so platforms like this in general make it much easier to input the variables you want with the constraints that you want, right? You don't want to have to figure out how do I get this arrow exactly on that block sphere, how many iterations it's going to take. If you're, in a finance, if you're in a bank or in that, finance skunkworks group, you just want to put in the algorithm. You want to get that result out. All right, so here is hardware rare synthesis. This one's fun. So here we're just doing an adder, and all we're saying is just add up the first 2 qubits on the left, first 2 qubits, 1, 2, and 3, 4. We're just adding all of these together. We're not doing anything fancy to it. And we're specifically saying we're going to synthesize this circuit with the constraint of, I plan to run this on IBM Quantum's Tokyo computer. That is my constraint. Instead of a number of qubits, instead of number of depth, I'm optimizing for this system specifically. So it's going ahead, and the system understands and knows the circuit connectivity of these computers. It knows the gate set, what's naturally available on that quantum computer, and it's going to go ahead and generate your circuit for you. Actually, let me stop that and keep going. There we go. Huzzah. Where we go? Let's do that one more time. it gave me a circuit, but I don't know why it gave me an error. Anyways, so it's going to go ahead and generate that for IBM's Tokyo. Dum, dum, dum. Oh, it already output that. Cool. Yeah, okay, so that went ahead and ran. Now we're going to go ahead and see what is the circuit we generate for it. And along with that, it's going to show you, when I go back to the other slide, the other page, is what is the circuit connectivity map of the circuit that we generated? Not of the computer, but what is our circuit connectivity map for that generated algorithm? Let's collapse that. Perfect. All right, so we have this system, and we can see this kind of addition is what's called a ripple carry adder. So it decided to choose this implementation for the circuit. Here is our circuit connectivity map for our qubits and how they map to each other and how we need them to communicate in our circuit, or at least how we've defined their communication. And then we can go ahead and say, you know, let's actually check what the circuit connectivity map is for this computer and how it maps up. Okay, so that's how that would translate out there. Perfect. So you can see how your circuit will map to that hardware.
Yeah, so what you're seeing here, like each dot is a qubit, and the lines connecting the nodes, these are the connectivity, the connections that you have between the qubits themselves, right? So this one can talk with this one, but it cannot talk directly with this one, right? So you need to pick the qubits that have, first of all, you need to have sufficient amount of qubits, but you need them to be connected in a way that lets you do run the algorithm. And the color coding is like how much you utilize them, like how much you use them, how connected they are to the rest of the qubits involved. So it's like one in the middle is kind of involved in a lot of the calculations is going on compared to the ones on the sides.
Yeah, absolutely. And this is some of the power also of these higher level programming languages and these platforms that facilitate it. It also allows for analysis, right? Yesterday when we were doing, building these circuits, we didn't analyze it to this degree, right? We built our circuits, it ran, okay, we're done. That's not how anybody programs software. You need to analyze it, you need to review it, you need to debug it, you need to say, is this, sufficient for me, or do I need to iterate on this? And so we have a couple of other things. You can go ahead and, similar to circuitry, you can plot out the heat map for this circuit and see kind of where your coding chunks exist in that diagram space. And that tends to be much more important when your quantum circuits get much, much larger, so you can see where these things exist in space. You can go ahead and plot the gate histogram to figure out, for your qubits, how are you utilizing them? How many operations are using multi-qubits or single qubit operations on those? So you kind of see where is your load on these qubits? Do you want to be using qubit 5 more than the others? Because each individual qubit on these computers have different fidelity rates, different, essentially, times before they start becoming error prone. Not all of them are made the same. And so sometimes you might want to say, ooh, I don't want to use 5, I want to use 4 or 3. Thankfully, the classic system handles that for you, so you don't have to try and figure that out and cherry pick which qubits to use for what. I think I talked about this earlier with some of you, but also you can go ahead and analyze your quantum circuit and see what would it look like run on different hardware. So if you just built your circuit and you want to see which hardware should I run my circuit on, you could generate this table. I'm only doing it for Microsoft and IBM here, but we have AWS and all the other vendors. You can see all their hardware tables. It just takes a little longer to go for all of them. And here's all your devices and what the depth would be, the multi-qubit gate, the total gate count. But for us to demonstrate this, I'm just going to optimize and filter it by depth. And we see that, thankfully, the computer that this is optimal to run on is the computer we optimized it for, right? IBM's Tokyo. Perfect. We optimized for this hardware specifically because of its gate set, because of its circuit connectivity mapping, and it happens to be that if we ran it on any other computer, it would be worse because they're all different. And sometimes it's really important to optimize for the specific hardware you're going to be running on. And this can change too, right? What if I want to change hardware vendors, right? I'm going to use Microsoft Azure's IonQ available device. Normally, this would require programming your whole circuit in a different assembly language. right? You'd have to figure out how to optimize for this whole other computer. What are its gate sets? What's its circuit connectivity mapping? But with this platform, you just say, I'm just going to change it and see what it looks like if I run it on this instead. It's plenty of fun, right? You can download images of this in interactive circuits. So you can actually download an HTML version of this if you want to just save. A lot of universities use this for various reasons, just to show off some of the larger circuits. But here's our adder, nothing fancy, but instead of what we did before, that ripple carry adder, we're using quantum Fourier transform adder. You see the QFT blocks here, right? This was our previous circuit. This is our new one. They do the exact same thing. They're just optimized for different computers. This one has a circuit depth of 37, a little bit shorter, a little bit longer than our 36 here. Let's see, this one uses 6 qubits, this one uses 5. How are we able to get there? Let's go ahead and see the circuit connectivity mapping for this. Why are you angry at me here?
You're missing. You have
What am I
the
missing?
analyzer after the brackets.
How did I do it before?
Isn't it like a new command?
Yeah, is it a new command? New circuit. Dum dum dum. All right, let's see. Did it a second ago. Show circuit, analyzer, plot qubit connectivity map. I don't know, let's do that. Scroll down. Oh, the fun of doing this.
Just click enter.
Just click enter.
Or like new.
Oh,
Then after new circuit parentheses, then you need to.
yeah, let me. New circuit what?
Here you need to click enter.
Oh, click enter here.
Yeah.
Oh, yeah, two different commands.
Uncommon there.
No, thank you for that. That's me not seeing things straight. Perfect. Thank you. Okay, perfect. So here's the circuit connectivity mapping for the circuit we just developed. It's much more interconnected than our last one. And we can see, why is that so? So let's go ahead and see what the circuit connectivity mapping for this IonQ device on Microsoft Azure ends up being that it's entirely interconnected as opposed to the last device. And that's because it's a fundamentally different technology. This uses ion trapping, and that technology enables all their qubits to talk to all of their qubits as part of the technology itself. It's kind of fundamental to that modality. And so where we couldn't use a quantum Fourier transform before, that's more efficient for qubits, we couldn't do that for the Tokyo system on IBM. We can for this one. And so different implementations are possible on different systems because of what the system is fundamentally capable of, right? This one can map more interconnected, and our circuit required, right? Quantum Fourier transform addition requires more circuit connectivity. And again, we can do our hardware comparison table and go ahead and see that. What you're going to see is the same exact thing that we saw before, that because we optimized for this specific computer, if you ran it on anything else, it would be non-optimal. It is optimized for IonQ's Azure system. Perfect. Love it. And again, the benefit of all that is I didn't have to learn how to optimize for one. I didn't have to learn, essentially all the minutia that it would take to figure out translating one implementation to another implementation, optimizing for different parameters. Again, we're letting the system handle that. I know what I want it to do. I'm going to let the system figure out the how.
If you think about from business perspective, we build an algorithm. Now we think about deploying it. And then you start to think about the cost for the organization. So you can do this analysis and say, guys, if we do the breakdown and we decide to go with IonQ and not with IBM, we expect to save $1,000 a day just for switching to a different provider. Mm-hmm. And it's not constant because IBM will soon release a new QPU, right? So you can do this analysis once again and say, okay, now we can go with IBM because their new system will actually drop the cost for us. Yeah. It also gives you the opportunity to choose, okay, my organization works more with Microsoft Azure as a web provider, like the cloud provider. Maybe just for this type of activity, we want to buy some credits from AWS and run it on using AWS on different systems that they have online and Microsoft doesn't have online. And so these are the kind of decision making that you can influence in the organization once you decide to start use this technology.
Absolutely. There's definitely the cost consideration. I find that a lot of companies, when we're working with them, it's can we run it today even, right? Some of these problems that people are generating are 50 qubits or very deep circuits, and they just need to know what hardware is there available that I can actually do this computation on. And so having that, that mapping and figure out I could run it on this one or that one, and it would actually run, right? You can optimize for different systems and see, what is your circuit most optimal for, right? Both for cost, but also for, I want to wait for next year's quantum computers. Can any of today's quantum computers do what I need it to do? And I'll show this before I go into this fun example, right? So we have this algorithm, right? We have this circuit we developed. In the system, you can also go ahead and execute it, right? It's with these modern platforms, it's fairly seamless to go ahead and run your circuits. So I'm going to choose AWS Braket here. I could choose IBM or Azure or any of these other cloud-based quantum computing providers. I'm going to say I want to run on their simulator just for speed and for time, so I'm not spending too many credits on our end. I'm going to use their SV1. I'm going to say I want 1,000 shots here. You can do different optimizations, but for brevity, I'm just going to run it. Here it's asking for all of my fun credentials, and thankfully I have my cookies, so I'm just going to go ahead and connect that. Quickly zooming through there so you don't see all my login credentials later on. Yeah.
We have the recording.
Yeah. No. So we'll go ahead and we'll run that. And essentially, right, that's it. The system is running this circuit on the hardware or on the platform of your choosing. Because it uses your API key and things like this, it knows to go ahead and use your account when it's running this. So if it requires credits, it's going to charge you the necessary credits to run the circuit. And all within the platform, right? You didn't have to move around. You didn't have to figure out what's the execution command for this hardware? How do I tap into it? How do I connect with it? What's the coding for it? Certainly some of these modern programs are enabling things like this, right? So like I said, this is actually a fun new tool that our developers came out with, making it even easier than all the Python things we've been working on to interact with quantum circuits. I've been showing you how to generate these circuits using Python, but in the platform, right, we can go ahead and synthesize them, right, generate them automatically, analyze them, and then right here in the platform, execute them. So I'll wait a couple of seconds for this to go. I was in the queue for a little bit, so it took me a second. And here we go. Oh. Interesting result. So yeah, the addition came out to be one solution. Okay. We could run a different thing, but here is our kind of synthesis platform. Makes it a lot easier, your coding. I'll just go into the Hello World program. And it kind of just already chunks some of your code out for you and asks you, what are your probabilities you want? What other functions do you want to put in here? And on the side, it just asks, the left, what do you want it to do? The right, what are the constraints you want? And you can go ahead and change this and say, actually, I want to add, an optimization parameter. I want my optimization parameter to be depth, and it's going to add that to the code automatically for you, so you don't even have to mess around with figuring out how do I put the optimization. You just have to say, what are the functions you want it to run? There's plenty of other fun preferences. You can go ahead and say, I want to optimize for this backend service provider, IBM or AWS. Synthesize it from the system, right? You didn't need to do any of the, pip installs. You didn't have to do any of the import commands. It's all in this integrated development environment. It synthesizes it for you, right? Like we showed, it's 3 state preparations here is what we called out. And then I can go ahead and the same way we did before, I'll go ahead and, just because it's already loaded into the system, I'll do this SV1 from AWS Braket. Again, loading this up quickly. Run. Dum, dum, dum. And I'm back in the queue here, so it's putting me in the queue. I don't know how many people are trying to also run on SV1 right now, but that depends on how long it loads. When you actually use other people's systems, sometimes the queue can be long, sometimes it can be short. But you can always go on their platforms and just see, you know, how long is the queue, what's the charges, things like this. See those actual practical considerations.
I have a quick question. I mean, while waiting for it to load,
Yeah.
between, when kind of evaluating quantum computing platforms, what are some characteristics or qualities we should look out for to differentiate one over the other?
Absolutely. You know, let me go ahead and, while it's loading even, I'll go ahead and load this up. I'll show you my AWS account. So I'm going to go in here, I'm going to authenticate as myself. I'm going to go into my AWS account, Classic. Yes, Management Console. And here I'm going to go into Amazon Braket. And you can go ahead and investigate all the devices available to you. So here it's saying most of them are available, one's offline, a couple of them are being cleaned up right now, so they have a timeout. But you can go ahead and investigate this and see what are those hardware, and you can click on these and investigate them further, right? IonQs.
Right, so I think in terms of picking, let's say if I'm kind of thinking which platform I should choose, I should choose one that has the most connections with different vendors. Is that how? So if a platform has access to maybe the top 5 largest quantum vendors versus one that only has 3, the one that with 5 is superior. Is that how I should evaluate platforms among all these platforms?
Yeah, I would say there would be 3 criteria. If you're a business and you're trying to figure out, essentially, you know, I want my developers to work in one of these environments. I don't want them working in all of them at once because that might be tedious or too much time that you don't want to take them away from their other tasks.
Yeah.
I'd look at 3 criteria, right? The different platform vendors all have different infrastructures on how you interact with the quantum computers. Some have integrated development environments. Some have, portals in them, right? Like, what was it? IBM just came out with, was it IBM? Yeah, IBM just.
The resource estimation.
Dell? No. Yeah, I think Dell was the company that just came out with a new interface for quantum computing. They just came out with a new platform. I believe it's Dell. Don't tell me if I'm wrong. They'll see the recording. They have different interfaces that you can interact, right? Some of them have Qiskit already embedded into their platform, so you can use Qiskit in their system, in their ecosystem, and then interact with the hardware. Some have different modes on how you can do that, right? AWS has their own kind of infrastructure where you can go ahead and communicate with these different computers all within AWS Braket without leaving it. So that would be one, that interaction. 2 would be, what hardware is available for you to run on, right? You want to go ahead and investigate this and kind of click on each of these computers and see, all right, this is 11 qubits. 11 qubits with all interconnectivity. So even though it's not a ton of qubits, it's really robust in what it can do.
Can you explain again what's the benefits of the interconnectivities?
Yeah, you could do more things, right? Essentially, if I build a circuit on this, I'm sure it's going to run the way I designed it. When it gets transpiled down, I know that all the qubits connect to all the qubits, so however I drew my diagram, it's going to translate, correctly and authentically to this system instead of having to be transpiled into a different gate set or moved around to run on that hardware because qubit 1 didn't talk to qubit 2, but in my diagram I said they do.
Connectivity is basically when you take one thing like sphere or I don't know what, and then another sphere and compare them or move them into a gate to see the result. This is the
You
connectivity.
can make them interact, like as entanglement, as you can use them and operate on both of them if you do multi-qubit gates, right? So for example, basically connectivity gives you flexibility in how you can run your code, right? So for example, let's say that we disconnect these 2, right? So now if you somehow the algorithm ran that you have some information state on this qubit and on this one. And you want them to do something together, but they are disconnected, right? What will happen is that you need to use a swap gate, kind of like swap the information between 2. So you need to move the information maybe here, and then you can make them talk to one another. So it adds another step just to shuffle everything around, so you can have things one next to another so they can talk to one another, right? So if you need to do those movings around, it makes your circuit more deep, or you need to use more qubits, or all this kind of stuff. So if it's really interconnected, maybe you can find a compact way of expressing your algorithm.
But in the hardware level, like I see atoms sitting in a room and the laser shooting at them or probing them. So I'm trying to figure out what is the actual connectivity means.
So let's continue with your way of thinking about it. Right? Let's say we have a grid, right? And you have, let's say, okay, and here in the middle, these are your qubits, right? So you have 9 of them. I started my calculation. I have some state here, and some of my state is here, because this is how the algorithm runs. Now I want these two to talk to one another, or to combine them. Let's say that I want to add them as numbers, right? And let's say that I have states on the other qubits, because I'm using all of them, right? What you will need to do now, because these two are not connected, let's say you can just talk to the neighbors, right? What you'll need to do is shoot the laser on these two and switch places. So there is a way that you can move the yellow one here, and now you move this one here. And now you need to do this trick again. So maybe you switch these two. So you bring the red one here, and you switch places with this one. Now they are connected. Now you can make something, and you shoot both of them, and you do the calculation on them. So if you have more connectivity, you need to do less of this moving around stuff.
Absolutely, right? And that messes with your qubit coherence time, right? The more operations you have, the noisier they get. You're just adding more time steps, more operations into your circuit that if you had a more interconnected quantum computer wouldn't be necessary.
By the time you're moving those folks around, the other qubits are just waiting.
Yep.
Right, and waiting means you're wasting time, and time means you're messing your results. So there are advantages for this. There are also disadvantages, but this is like one of the good things that comes from this type of modality, using trapped ions.
Let's see. Yeah, let's also take a look at Oxford's. So they are universal gate-based. Here's the topology. Oh, it just talks in a circle. They're not interconnected any other way. Each of them has 2 connections. So, yeah, so to answer your question, I would look at 3.
Question 2, infrastructure, interconnectivity. What's the last one?
Costs. I'm taking a look at this number here. Per task, per shot. What is the cost to actually run on this hardware, right? What's it cost to buy, Amazon Web Services credits? How many operations will that allow my team to use? Essentially, what's that costing my corporation for using this interface? Yeah. So yeah, that would be the 3. I would say the interface itself, what's available in there on how it lets you communicate with quantum computers. Some have, nicely developed interfaces. Some just say, here's an API key and use your Python notebook to do it on your own. The second would be, what computers can you actually hook up into? The third would be the cost.
Okay, thank you.
Yeah, absolutely. Okay. Boom, boom. Perfect. Oh yeah, this was just a fun example. We can go into it if you want, but this is an applications of Grover's algorithm. Right, Grover's algorithm looks at an unstructured data set and finds you essentially the solution you're looking for. So this was a fun one. I think one of our colleagues actually wrote a blog on this for Microsoft Azure. Doing a Secret Santa, right? We have certain criteria. We know that the same person can't give a gift to themselves, and we can't have more than one person getting, you can't have one person getting more than one gift. So with those 2 criteria, we have our constraints for that problem, and then we can kind of go ahead and execute our solution. So here is how you would define this, right? X1, not X2. So we have X1, but not X2, right? Allie can give a gift to one or the other, but not both, right? The same, Bretta can give one to the other or not. And so at the end of the day, if you did this logic enough, here's all of your constraints, your formula, right? This, but not this, this, but not this, right? You have to pick one of these, but it can't both exist. So yeah, these are, if you're doing Boolean logic, those are just XOR arguments. And the way you would put this in the system is, here's your formula. Dum, dum, dum. I'll just copy and paste it. Instead of having this be academic, let's run it. Wow. All right, so here's your formula. We're saying that the input size for each of these variables is going to be 1. It's either 0 for they don't get a gift, or 1, they got a gift. So we don't need multiple qubits for each of these parameters. Yeah, this is just saying, we defined it with this kind of up arrow, but the command is actually a XOR argument. Here's our registers. We said it's all going to be just 1. I'm going to go ahead and optimize the circuit. There's different uncomputation methods you can use for Grover's algorithm, but we're going to go ahead and just use the most optimal, because why not? And I'm going to go ahead and execute this, right? So when you're executing with Grover's, you have to use the amplitude amplification algorithm that was talked about before, and the system handles that for you as well. So we're just going to go ahead and run that. We're going to see what that circuit looks like for generating a Grover's algorithm. This one I like to show in general, because if anybody's ever gone through that whole Qiskit environment and they get to Grover's, they know how painful it is to generate this kind of a circuit. It's a beast of a thing. I'm still trying to get the hang of it. Yeah. Because there's a bit of the circuit called the oracle, and you have to put in all of your constraints in a way in there that I have not yet mastered. So here we just generated a 15 qubit circuit in what? Definitely less than a minute. So here is our arithmetic oracle. Here's what we call the mixer on the end. And here is all the arguments that we put in there. So here's the bitwise XOR argument. And what is a bitwise XOR argument? Well, it's a bunch of C0 gates. And that's pretty much it. That's how you input this into the system. This but not this, this but not this, this but not this, this but not this.
And this is only for 3 players?
This is only for 3 players.
And if I go to 10 players, 20 players, how many qubits do you need?
That's a great question. You know what? I did this article a little bit ago. Let's just have fun with this. Let me go to our website. So, oh yeah, I was looking up recently, 715. We wrote an article because we had a quantum competition recently, and we challenged people to go ahead and solve a very similar problem. It's called a Kokoro puzzle, kind of like Sudoku, right? And so it has a rule set to it. You have to have these numbers here. And so we have this Kokoro puzzle, very similar to Secret Santa we were just talking about. And it's just a bunch of those arguments. Actually, some of the contestants had a hard time translating this into the argument, so we just, don't worry about the picture, here you go, here's the arguments. We don't want that to be the part that's challenging for developing optimized quantum circuits, because the challenge was develop the most optimal, shortest depth quantum circuit possible for this, right? Showing that we're just kind of showing that it's not easy to create optimal quantum circuits. It takes a lot of education, PhD level people to try and attempt this, win these kinds of competitions to create optimal circuits. And so we did this, and after the challenge was over, we showed how you would do that on the classic platform. Cool, you do all that, you type it all in, you export it. Here's our our circuits that you generate. Okay, so that was a 29 qubit circuit to generate that. But actually, me and Hannah, the other person in the US in marketing with me, said, how far can we stretch this? Can we have some fun with this? So we just asked our developers, send us 100 clauses. Right, send us 100 of these clauses that don't argue with each other, right? Send us 100 of these clauses and we'll test it out. And we just typed in 100 of these into the expression, right? The same thing, here's my expression. I have 10 of these things going on, and we went and generated it, and the system came back with a 715 qubit circuit. It did it. You can't run this on any hardware that exists today. You can't even run it on a simulator. We don't have simulators powerful enough to do this kind of a thing, right? So, actually, no, 715, Condor just came out, 1,000 something. We could run this today.
Still not, I think, online, but maybe really soon.
But it exists in the world.
I
Yeah.
think like maybe a more technical answer to your question, the amount of qubits that you will need to add moving from 3 players to 10 players is far less than the amount of resources you will need if you want to solve it with a classical computer. Right, so if you remember yesterday we had this graph about how many qubits you need or like how much can you express using qubits, right? So we say that classically it's scaled like 2n, and with qubits it's scaled like 2 to the power of n, right? So you can pack more information with fewer qubits than you can do on a classical computer. So for this type of problems, you will see an advantage.
Absolutely.
And it's like, it's a fun example, but if you think about it, it's basically kind of integer binary optimization problem, right? And we do it a lot, right? I want to open new distribution centers, and I want my distribution center to cover no more than 3 cities. Like, where do I put my distribution centers? How do I make my factories use their capacity, like move stuff around? Maybe I need to shut down a facility. So its bit integer will be 0. So you know, okay, I need to shut down this facility, move it somewhere else. Right, so it's a fun example, but it can be generalized to a lot of problems when you have these binary decision variables.
Just tactically, should you always optimize for depth or should we optimize for width?
Depends on your needs. Right? If you need to work with specific QPU and this is the amount of qubits that you have, you need to make sure that it fits in. If you can choose whatever you want and you know that the qubits are noisy and you really, really care about the accuracy of your result, you want it to be shallow circuitry and use more qubits.
Okay, so accuracy. What if I want speed? Should I then do it this way?
Speed is also, you want it to start and end quickly, so you want it to be shallow, less actions that you need
So
to
I should
take.
always try to make it, so I should always make the depth as short as possible. I should always optimize for the depth.
As long as it can run on the hardware you want it to run on, right?
If-
Number of qubits can't exceed.
Got it, okay.
Yeah, so typically when we work with companies that haven't already decided on a vendor or a computer to run on, we tell them first generate the circuit and then we'll take a look at it. After that, we'll say let's optimize for the number of qubits. You know, if it ends up being something that takes like 50 qubits, we'll say how thin can we make this circuit? Once we figure that out, we can say, okay, you can run this on this hardware, and this hardware. Let's optimize for those hardwares and see how short we can truncate it, right, within the number of qubits available on those hardwares. So that tends to be kind of the path we take with them. Let's see the circuit, let's see how thin we can make it, and then let's optimize for the hardware that has that many qubits that can actually run this bit of software.
Okay.
Yeah. Absolutely, and like I said, like we were saying, this is a fun example, but also what this is demonstrating is nowhere in the calculation, nowhere in the input did I say, how many qubits I had. I didn't say, it wasn't a huge bit of code. All that changed was my the expression I'm trying to solve for, my input variable, right? The thing I'm solving for just got larger. And the circuit got larger. I didn't have to specify exactly how. I didn't have to worry about it. And so what this is showing that by defining things at this functional level, by saying I have a Grover's algorithm, I have an oracle that needs to solve this expression, no matter how large the expression is, it's going to give you a circuit that solves that. So it's scalable. It doesn't care how many resources it requires. It'll give you that circuit. It might not be something you like. It might not be something that you could run on today's hardware. But that then shows you, right, let's maybe go back into it. Can we simplify the expression? Maybe we can sacrifice some of the accuracy to make it fit in. Are there other ways to express this same criteria that could run on the system a little bit more efficiently, right? certainly this happens every day in physics problems, right? You have this gargantuanly complex system, and it would take you a year to solve this equation. Let's round some of this out. Let's simplify or assume, certain things. Like my favorite example is to assume that a cow is circular, right?
Sphere.
Yeah, a cow is a sphere, right? Physicists often make these kinds of assumptions to make calculations easier, but they do it within reason, right? I'm okay with this assumption because my result will still be applicable enough for the thing I'm trying to do, right? I don't need it to be exactly right. I need it to be right enough. And so this allows you to figure out, well, let's go back to the expression, figure out how right I need it to be, and then let's see, can that run on the quantum computer and try to run on? Yeah. Yeah.
Can you have, can you set limitations to your algorithm to say don't use a specific gate?
Yes. You can go ahead and essentially say, you would optimize it and say 0. Make me a circuit with 0 of this gate.
Yeah, okay.
Yeah.
Nice.
Absolutely. Yeah, I mean, and that happens, right? People want certain circuits, and it might come back and say, actually, it is not possible to do the thing you're trying to do without that gate.
Yeah.
So.
And, right, okay.
Totally. Yeah. So hopefully we've seen today, exactly. So we're going to end here, and hopefully we saw that yesterday was painful programming on, right, we got to 2 qubits at the end of the day, doing it by hand. Here, with simple, simple bits of coding and simple arguments, we're getting to 50 qubits quite easily, generating, running quite seamlessly on the system. You can get to hundreds, thousands also. And right, these higher level programming languages, these new modern platforms are enabling hardware that's coming out today, right? You don't have to program at the assembly language. You can actually output code in minutes or weeks instead of months or quarters of years. It would definitely take that long probably to program on Condor, but yeah, hopefully you see kind of the future of quantum computing and what it will take to program and use it, right? If you are starting a business and you have your software developers, it's not all that different from Python or other environments they're working on. It's not so far a stretch anymore to do these optimizations. They don't need to have PhD level physics degrees to create really good optimized circuits that run and do what you need it to. So hopefully we'll all generate a lot of good revenue out of quantum computing soon and do all this fun credit risk analysis in not too long. And if any of you make a business out of quantum computing, call me. We'll talk. All right, well, thank you very much, and I hope you enjoyed tomorrow's session. We're going to have a panel with AWS, Parminder, who is here. We're also going to have Sam from NVIDIA coming over, and we're just going to have a panel session, but we're going to have it be fun, informal. So if you have any questions you would like to ask AWS, NVIDIA quantum experts, I'm going to be on the panel here as well. Think of them. Come up tomorrow with them, right? You ask away. We're going to have fun with it.
I have a question right now. So it's more like on the physics side.
Yeah.
Entangling and disentangling particles, does it wear on the particles themselves, on the qubits? Like if you entangle them too often, can
If it breaks down, kind of degrade,
Continued operations.
theoretically everything breaks down.
I mean,
And I know specifically I spoke, it was like 2 years ago with the couple of IBM guys. They said that after you use the QPU for a while, you saw Eric showed you that there are 2 systems which are offline for maintenance. They need to do it more often, and it takes longer just to calibrate the qubits again. So it breaks down basically.
okay. And so you need recalibration.
Perfect. Okay. If anybody's here, feel free to ask questions, but we'll say class is over. You can go ahead and do your thing. I'm happy to stay here and talk if anybody wants to. And again, right, that's essentially what tomorrow's going to be too. So come up with fun questions. Save your hard questions for Parminder and Sam from AWS and NVIDIA. No, it'll be really cool and fun. Yeah.
Thank you.
Thank you for
Absolutely. Totally. Yeah.
Thank you guys, thank you for staying.
Yes, thanks.